Hello, wishing a good day. Today we will be presenting a paper on coloring in graph streams, and we are a group of four presented by myself, K.R. Anuraj, Raghavendra Kulkarni, Kunal Bagh, and Shubham Bhattacharya. The paper was published by Suman K. Bera and Prantar Ghosh, and basically it is vertex coloring in a semi-streaming model. I shall cover my presentation under following heads: basically, insight to a graph coloring, then the problem statement, and preliminaries that hold the complete paper, and the techniques that they have devised to get the results. Graph coloring is a fundamental problem in graph theory and computer science. It involves assigning colors to the vertices of the graph that no such two adjacent vertices share the same color. The main objective is to minimize the number of colors, and coloring the large graph, especially those with millions or billions of vertices, present scalability challenges. Basically, memory usage and computational time become very significant here. So problem statement as such is like the prime goal is to reduce the number of or the minimize the number of colors, or the using a few colors as possible in the semi-streaming settings. So semi-streaming model is a computation model in like algorithm or data processing for scenarios where a dataset cannot fit into the memory, but allow random access. It aims to minimize the memory usage while providing accurate solution using techniques as we learned in the class, like sampling, sketching, and other approximation. In real world, we can relate to network analysis, machine learning, where traditional methods are insufficient actually. So as we know, there are different types of coloring mechanism. Vertex coloring, that is for the vertices, node to adjacent vertices share the same color. Edges, for that sake, node to edges should uh, share the same color. Then the phase coloring, like in a planar graph, that node to adjacent faces share the same color, and a combination of vertex and edge coloring, which is a total coloring, where adjacent vertices and edges are assigned different colors. So some of the challenges that will be mainly through this on the semi-streaming settings, basically is in terms of memory constraint, where model will be dealing with limited memory resources, so the entire graph cannot be stored in the memory at once, so which will have affect the efficiency and accuracy of the solution. And one pass constraint, basically in the semi-streaming model algorithm typically have only one pass, so and information once process won't be revisited, so without complete knowledge of the structure, the decision problem would be at stake. Approximation, because of the limitations and algorithms to find approximate solution than optimal solution. So there is a trade-off between accuracy of for efficiency and are designed to work within the memory constraints. Then balancing the color and the memory, again another which is crucial for the effectiveness of solution. And data arrival order, like data might be in our setting, like the paper would define the data arrival order in adversarial order, where here like the actually the processing of data can affect the algorithm decision, and it must be adaptable to the arrival of the vertices and edges. And graph can be having a dynamic scenario where vertices and edges being added or removed over time. This must be able to handle these dynamic issues also. So we have some preliminaries which will hold throughout the graph. So as in a normal case, we have a greedy algorithm, like we have a delta plus one color, where the intuition is if a graph having a maximum degree of delta, and then no vertex can be adjacent to more than other delta vertices. So by assigning each vertex a color different from its neighbors, delta neighbors, we ensure that no two adjacent vertices share the same color. So this implies that delta plus one colors are needed to properly color the graph. This is a general greedy approach. But in a semi-streaming approach, where this is a difficult situation, so we are having set of preliminaries that defines the this thing, the tool, basic tool for arriving at the result. We have stream of edges income in adversarial order, and we have a cache register variation where once added edges once added won't be removed, and we have orientation of edges, and degeneracy of graph, arboricity of an undirected graph, and vertex coloring, which I shall tell in brief. And orientation of edges is basically a constraint that is kept so as to in order to preserve that coloring property within a vertex color. Basically, orientation for a graph edge might introduce additional constraint or consideration to into the vertex coloring problem. Basically, a coloring algorithm might need to ensure that for any directed edge from vertex A to B, A has different color than B. Degeneracy, a graph G is K degenerate if every subgraph H of G has a vertex degree at most K. So a graph is bounded degeneracy is a graph in which every subgraph has a vertex with low degree compared to the number of vertices in the subgraph. Bounded degeneracy graphs are commonly found in real world application. We have social networks, communication networks, etc. Arboricity of an undirected graph is the minimum number of forests into which edges of the graph can be partitioned. So basically, arboricity and degeneracy are indeed very closely related concept in the graph theory. Both characterize certain properties of the graph related to their sparsity. Both arboricity and degeneracy are measures of sparsity of the graph, how dense the graph uh, uh, can hold it. So suppose a graph with low arboricity or low degeneracy is relatively sparse, meaning it lacks dense substructures. Here we basically we can achieve another relation. The arboricity of a graph is bounded by one or more than its degeneracy, which is again a close relation between these two. And finally, the vertex coloring, as we already defined what exactly a vertex coloring is. Chromatic number of a graph is denoted by uh, it's defined as a minimum number of colors. So this minimum number of colors is the minimum number of colors that we need to hold to color a graph. So this is a very it's an NP hard problem to find. So we arrive finally at two techniques under two algorithms that we define in the paper. Um, in one, so there is a 1 plus epsilon delta coloring vertex coloring problem, and which is defined. So this is a randomized one pass streaming algorithm. So which will find uh, using an order of n polylogarithmic amount of space. So the algorithm achieves a coloring that is in within a factor of 1 plus epsilon of the optimal coloring in terms of maximum degree. Now, with respect to the arboricity, we define another algorithm where there is a randomized, which is order of 1 by epsilon log n pass streaming algorithm that finds 2 plus epsilon alpha, that is the alpha is the arboricity of the graph, vertex coloring of the input graph using order of n amount of space. So the this actually the space constraints are less stringent here, but it offers a high quality coloring, so which reduces again the minimizes the coloring throughout. So in the further presentation, in the next part, Raghavendra will briefly describe about 1 plus epsilon delta coloring algorithm, followed by Kunal and Shubham describing about 2 plus epsilon alpha vertex coloring algorithm. Over to Raghavendra.
Hello everyone, I am Raghavendra Kulkarni. We will now be discussing a vertex coloring algorithm for graph in streaming setting. We discuss a 1 plus epsilon delta vertex coloring algorithm for a graph G where delta is the maximum degree of a vertex in the graph and epsilon is a chosen constant. The main three characteristics of this algorithm are: it is a one pass streaming algorithm using O tilde of n space or n polylog n space. The algorithm assumes that the value of delta is known to be sufficiently larger than log n before the arrival of h stream, where n is the number of vertices in the graph. Also, the algorithm colors the graph in two different phases, say phase 1 and phase 2. These phases are discussed in the following slides. Phase 1 coloring. We first set the value of L to be the seal of epsilon delta by 2c log n and then take L different colors, say 1, 2, 3, 4 and so on up to L. Then we color every vertex in the graph by choosing a color independently and uniformly at random from these L colors. Since this color selection is at random, phase 1 coloring may not give a proper coloring of the graph. That means there is a possibility that two vertices having an edge between them can have the same color. Say we have a graph as shown on the left and we assign each vertex a color from a set of four different colors. Note that this is not a proper coloring of the graph. But Now we group all those vertices into one which have the same color. This will give us L different subgraphs, in this case 4, and some pairs of vertices in a subgraph may have an edge between them, as we can see on the right side of the slide. Now we move on to phase 2 coloring. The algorithm claims that the maximum degree delta for any vertex within a subgraph is order of log n, that is big O of log n. So we know that any graph with a delta in order of log n can be colored using delta plus 1 colors, and there is a greedy algorithm to do so. So we now start scanning the edge stream and color these subgraphs parallelly using a unique color set for each subgraph, with each color set containing delta plus 1 different colors. Here delta is the maximum degree of any vertex within a particular subgraph. This is phase 2 coloring. So this is a epsilon plus 1 delta vertex coloring algorithm with two major steps. Pre-processing, which is the phase 1 coloring, and stream processing, the phase 2 coloring. We can see that in pre-processing, the algorithm sets the value of L and defines a set of L different colors, then does the random assignment of colors to these vertices. As claimed before, the delta for any subgraph is at most 1 plus 2 by epsilon C log n. Set this value as R and take L different color sets with R plus 1 colors in each set. Note that these color sets should be pairwise disjoint. Then, as a part of stream processing, scan the edges for every edge. See if the vertices have the same color or not. If they have the same color, then they must be belonging to the same subgraph. So reassign a new color to any one vertex from the vertex color available from the set belonging to that particular subgraph. Else, we can ignore the edge. The lemma. We now prove that the maximum degree of any vertex within a subgraph is at most 1 plus 2 by epsilon C log n. So let us take a subgraph where all the vertices have the color I. From this subgraph, let us take a vertex V. For any neighboring vertex u of V, let yu denote 1 if u and v have the same color and 0 otherwise. And then let xv denote the sum of all these y values for all the neighboring vertices u of v. The expected value of xv is of course the degree of v divided by the number of subgraphs. So it would be xv divided by epsilon delta by 2c log n. When we substitute the maximum and minimum value for degree v, we get the maximum and minimum value of this expected value as 2c by epsilon log n and 2c by epsilon into log n by 2 delta. Now we pick an m from the range 1 to delta such that the expected value of xv lies within 2c by epsilon into log n by 2m and 2c by epsilon into log n by m. We now calculate the probability of this xv being greater than 1 plus 2 by epsilon into c log n. By rewriting the RHS of this inequality, we can substitute it with the expected value of xv and probability inequality still holds. This value by Chernoff bound is at most e power negative 1/3 of 1 plus epsilon by 2 into m minus 1 into expected value of xv. With some substitutions and mathematical simplifications, we see that this expression simplifies to e power minus c log n by 6. Since we can choose the value of c, we choose it to be 66 by log e. Note that the log here is to the base 10. So simplifying further, we see that the bad probability of this xv being greater than 1 plus 2 by epsilon into c log n is at most 1 by n to the power 11. When we sum this inequality over all the vertices, the total probability will at most be 1 by n to the power 10. So we prove that probability at least 1 minus 1 by n to the power 10. With this probability, every vertex has at most 1 plus 2 by epsilon c log n number of neighbors with the same color, thus completing the proof. So the main theorem states that there is a randomized one-pass streaming algorithm that produces a 1 plus epsilon delta vertex coloring of a graph with a maximum degree delta using O tilde n amount of space for any constant epsilon. Furthermore, the worst case update time of the algorithm is big O of epsilon inverse log n. The proof of this theorem is straightforward. We know that the phase 1 coloring uses epsilon delta by 2c log n plus 1 different colors form the subgraphs initially. Since each subgraph has delta in order of log n, it takes at most 1 plus 2 by epsilon c log n plus 1 colors for each subgraph coloring. We multiply these two quantities to get the total number of colors, and this product further simplifies to at most 1 plus epsilon into delta. The amount of space used is controlled by the value of delta, and hence it is big O of epsilon inverse n log n. Also, since delta is big O of log n for every subgraph or subgroup, finding a proper color for a vertex in a group takes at most big O of epsilon inverse log n time. This completes the algorithm proof. Thank you.
Okay, so now we'll be talking about the second algorithm. It's actually a 2 plus gamma into alpha coloring algorithm, and it's a multi-pass or multiple pass streaming algorithm. So let's see what is the intuition behind it. So as we saw that in the previous algorithm, the availability of delta made our work very easier because delta is directly controlling the maximum degree of the graph. So once we have a control over the maximum degree, we can easily color the algorithm. Either if it is less than log n, then choose the algorithm, or if it is more than log n, then we use the 1 plus epsilon into delta, the previous algorithm. But here we don't have the delta available to us. We are only given the arcosity alpha. So what should be the idea? The idea is we need to use alpha to get a bound on the out degree of the graph. Now here I'm talking about out degree because we are not explicitly working on directed graphs, or we are not explicitly creating directed graphs. We will be working on undirected graphs only, but we will be following some procedures which will implicitly give an orientation to the edges of the graph, which will make sure that our out degree of the graph, implicit out degree of the graph, is bounded by some function of some function of alpha. So suppose I assume that we have bounded it. So there now what happens? There are two cases. Same cases as the earlier ones. If that bound, if that bound is less than log n, then we can run the trivial offline algorithm. We can store all the edges, we can store all the vertices, and we can run the greedy coloring algorithm and get a f of alpha plus 1 coloring algorithm in the offline sense. But if it is less than log n, then if it is less than if it is strictly greater than log n, then what happens? So in this case, just like the previous one, our algorithm will try to algorithm will almost use the previous algorithm, but instead, as we saw earlier, that we used to create something epsilon delta by 2c log n number of monochromatic subgraphs. Instead of that, we'll not using this. We'll be creating some order of alpha log n number of monochromatic subgraphs, which will actually give us the bound which we wanted. So you can notice that our algorithm can be partitioned into two parts. The first part is the partition of the vertices of the algorithm in such a way into multiple parts, which gives a control over the out degree of the graph, or gives a bound over the out degree of the graph. And once we have that information in hand, then you can slightly modify the previous algorithm and get a 2 plus gamma into a gamma coloring algorithm for that. Okay, so before moving on to the next slide, the question which comes is why alpha? So this, you can see that this is a result, fairly old result by Gary Chatran and some others in 1960s, uh, late 1960s, and it says that alpha is a fairly small quantity compared to delta. So in those cases, if we can bounding the coloring of the graph by delta is to some extent easy, but if we can bound it by alpha, it would be better. So that's why alpha is a good parameter for us. So this is actually our main claim. We will be seeing a randomized streaming algorithm. It will be a 1 by gamma log n pass streaming algorithm. The other things is it will be a 2 plus gamma into to alpha vertex coloring algorithm, it will be using those many colors. It should be gamma actually. In this case, it should be gamma, and it will be done. The main thing which we are concerned about, it can be done in OT-LOF and space, irrespective of all those partitioning and all those extra coloring process. That's what is the interesting thing here. So let's see each of the parts of the algorithm in a little bit detailed fashion, and then we will move on to the actual. We will analyze each of those parts separately in a more detail. So in part one, what the algorithm is doing is actually creating H1 to Hk k partitions, disjoint vertex partitions, where k is 1 by gamma log n, and it is ensuring that once we create such partition, vertex from any vertex in the particular partition has right degree, has its right degree at most 2 plus gamma into alpha. So this actually helps us to ensure that we have a bounded right degree on our out degree is somehow bounded, and once that is bounded, or once we have a control over that, we can easily color it. So, and one thing to note is that once we create such kind of partition where the out degree is bounded, you can see that it automatically creates an implicit orientation of the edges. So inter partition, like if an edge is going from one partition to another, we can orient the edges from a lower partition number to a higher partition number, and if it is going within a partition, then we can orient the edges from a lower vertex number to a higher vertex number. So this is a simple figure to get an idea of it. So assume that these vertices are numbered. These are the partitions H1, H2, all the way to Hk, and in each partition, the vertices are numbered in a non-decreasing sequence from left to right, like 1, 2. It is again 1, 2, 3, something like this. Maybe you can use different colors, but the main thing, it should be non-decreasing. So see, here you can see that this right degree is bounded. So this actually helps us in bounding the out degree of the graph. In the second part, now once we have it, in the second part, what we will do, so instead of doing this, as I mentioned previously, instead of doing this, it decomposes the graph into order of alpha by log n many monochromatic subgraph, order of alpha many monochromatic subgraph, and almost uses the same idea of the previous algorithm to color the vertices. So that's what it is doing. So let's see now we will see each of the algorithm in detail. So let's see. So what is the idea? Initially, we will be creating partition of the we'll be doing partition of the vertices, and those will be disjoint partitions. So disjoint partitions means the union of all those will be the entire vertex. So how we are doing it? It's a fairly simple greedy algorithm. So this is not the origin. This is not an algorithm from this paper. It's a paper it is a result which is given by Barron, Bowen, and Elkin. They gave it for a distributed environment, but we will see that it can be fairly transferred into, we can use it in a streaming environment also. So idea is quite trivial. So initially we have an entire set of vertices. Let's say it's V. We go through the entire stream once. We store all the degree of the vertices, and out of all those vertices, those whose degree is less than 2 plus gamma into alpha, we put them in H1. And once we create H1, we remove all those vertices who are part of H1 from the original set. So H1 is removed. Now in the remaining set, if this is the remaining set, if this is the remaining set, out of this, for the remaining vertices, we again go over the string, and for the remaining vertices, we again store the modified degree for them. And again, within them, if someone's degree is less than 2 plus gamma into alpha, we again store them into H2. Now, in this way, H2 is formed, and we remove H2 from the original set. H2 is formed. So in this way, we keep on going and removing vertices greedily from the original vertex set until we get all those partitions Hk. So this is roughly the main idea of the algorithm, and this is the exact snapshot of the algorithm taken from this paper we are presenting. If you want to take a look at it, you can pause the video and just take a look at it. One thing to mention is, see that as I mentioned, that once we get this partition, it will immediately create an implicit orientation of the edges, which is mentioned here. It is implicitly, algorithm is not doing it, but it is implicit in its sense. Implicit. Now the claim is, we will see that this is actually a k-pass algorithm. So now we will do the analysis for this partitioning algorithm. We will see that it is a k-pass where k is 1 by gamma into log n, and it is doing it in OT-law of n space. So the thing is, why it is k-pass? Because for creating each set, we need to go through that entire pass every time and note down the degree. And we are creating k many partitions. So that's why it is k pass. Why it is gamma by 1 by gamma into log n, that is beyond the scope of this presentation. It's involved proof. You can go and see in the original paper for that. For the space complexity, it is fairly easy to see because every time we need to store the degree, the modified degree of the remaining vertices who are yet to be chosen. That is not going to take more than O of n space, and we need to store a flag kind of thing which marks that what are the vertices which are yet to be chosen or what are the vertices which are already chosen. That is not taking more than O of n space. So overall, it can be done in O tilde of n space. That is fairly easy to see. So finally, we come to the end of this partitioning algorithm, which partitions the algorithm, which partitions the vertices and give a control over the out degree of the graph. Once we have it, now we'll see how we can use it and use it in along with the previous coloring algorithm we saw, and that will be presented by my fellow groupmate Kunal. Thank you.
Okay, let's continue the 2 plus epsilon into alpha vertex coloring algorithm. We have seen that this algorithm is divided into two parts, where in the first part, some partitioning algorithm was there, and in the second part, some coloring algorithm is there. Okay, and I will be discussing the second part, which is nothing but the coloring algorithm. From the first part, the takeaway from the first part is nothing but given a graph G with adversarial alpha and a small constant gamma, there exists an orientation. I mean, we can give always an orientation to all the edges such that resultant graph would be a DAG and the out degree of any vertex would be at most 2 plus gamma into alpha. Now I will be discussing the coloring algorithm, which is part 2. In the coloring algorithm, we will use the two-phase concept of two-phase coloring, which was used in 1 plus epsilon into delta coloring algorithm, which was the first algorithm in this paper. Okay, this is the two-phase coloring. So in the first phase, we decompose the vertices into big O of alpha by log n many monochromatic subgraphs. And in the second phase, we use the offline algorithm to color each vertices in the monochromatic subgraph. Okay, so here are two cases. When alpha is less than log n, then we know that we can store the entire graph using n polylogan space. So then we can use any offline coloring algorithm to color that graph. So that case is not that much interesting. Now let's take the case when alpha is greater than log n. So let's give you an overview of the coloring algorithm. So firstly, we consider a decomposition of the input graph into these many monochromatic subgraphs. So first we give a random vertex coloring to all the vertices to get these many monochromatic subgraph. And then in parallel we use the partitioning algorithm, which was in the first part, to get some partitions, right, which will implicitly tell us the orientation of the edges. And then basically store all the edges of monochromatic subgraph and color them in offline settings. Why you have to store the edges of monochromatic subgraphs? Because we need a proper coloring over here, and every edge of that monochromatic subgraph is colored same, so we need to give them different color. That's why we have to color them again in offline settings. Okay, this is basically the overview of the 2 plus epsilon alpha vertex coloring algorithm. Okay, so let's now discuss the main algorithm, pseudocode of the algorithm. Okay, so here is the preprocessing part. What's happening over here? So here we will get the L many monochromatic subgraphs. How do we get? We know that first let's set a value of L, where L set to this much quantity. It's a bit technical. We will discuss it later. Why L is chosen like this. So basically, first get L many monochromatic subgraphs. Okay, this is the preprocessing part. Now we will have gi monochromatic monochromatic subgraphs where I belongs to L. I mean, we will have L many monochromatic subgraphs. Now let's say edge is coming in the streaming mode. So if both endpoint of that edge is colored same, then we'll store that edge. Otherwise, we will discard it. Okay, so why we have to store that edges? Because as I have said earlier, all both endpoint of the edge is colored same. We have to give them different color. Okay, so after storing some edges, we will get another graph G dash, let's say. We will get another graph G dash, which is subgraph of G. Okay. Now, in parallel, we will also call the partitioning algorithm to get all these partitions, which will tell us the orientation of the edges. Okay. Now, in the offline settings, we will color all the vertices in each monochromatic subgraph, because we know that if a graph has delta out many out degrees, then we can color that graph using delta out plus one many colors. In a there is some offline algorithm to color that graph. Okay, so this is the main coloring algorithm. Now we have to show that this algorithm will maintain the streaming algorithm. Streaming algorithm invariant. What is streaming algorithm invariant? It's nothing but the space complexity. So within n polylogan space, we have to we have to done all those things. Okay. So in the first part, we have seen that this partitioning kind of thing can be done in O tilde of n space. Okay. This is the result of another paper. So we'll not discuss it here. And what we'll discuss is that coloring, that date storing kind of thing is used at most O tilde of n space. Okay, which comes from the following lemma. The lemma says that let delta out be the maximum out degree in oriented monochromatic subgraph. Then with high probability, delta out is at most some function of log n. Okay, for all I belongs to, I mean for all those monochromatic subgraphs. Okay, now let's give the proof of this lemma. It's a bit technical, not that difficult also. Okay, so let's take a random monochromatic subgraph and let's choose, let's say that graph is Gi. Okay, and let's fix a vertex V belongs to that V. From the fact that from the first part of this algorithm, we know that out degree of V is at most 2 plus gamma into epsilon. Okay, now for each out neighbor u of V, let yu denote the indicator random variable. Okay, so yu is equal to 1 if u has the same color as V, 0 otherwise. And let xu denotes the number of total out neighbor of V with same color. So what xv denotes? Xv denotes the out degree of V in that particular monochromatic subgraph Gi. Okay, so xv is equal to we know that this is the property of expectation. Xv is equal to, I mean, we will define this xv is equal to summation of yu, where u belongs to n out of V. Okay, so by the linearity of expectation, we can see that xv is equal to e of xv is equal to summation of e of xv. Okay, e of xy. Now, since probability of yu is probability of yu is equal to 1 is equal to 1 by L, where L is this quantity. So by linearity of expectation, we can say that expected value of xv is equal to out degree of xv by L, where L is this quantity. Okay. Now, since out degree of V is at most this quantity, so this EV can be bounded by this value. And we know that out degree of V is greater than 1 by 2. So again, x e of x uv can be lower bounded by this quantity. Now, since this is the upper bound and this is the strict lower bound of ev, we always choose 1m, which is belongs to 1 to 2 plus 1 to this quantity. We can always pick one such m such that this quantity holds. So we can see this from this line, where we can see that this is the lower bound and this is the upper bound, and here let's say this one is expected value of ev. So we will always get such m. We will always get such m such that this value is greater than this one and this value is less than, I mean this expected value is less than this one. Okay. Now, this is nothing but a calculation. So here we want to calculate that value of xv is greater than some function of log n is how much. Okay. So here we have seen that this is at most 1 by n to the power 11. Here is a bit calculation by applying Charnov bounds and by applying all those things, we'll get this one. This is calculation. There is nothing but a calculation. Okay. So we can see that value of xv, which was out degree of V in that monochromatic subgraph, is greater than log n is very low. Okay, which implies that out degree of v in that monochromatic subgraph is less than log n is very high. Okay, so by union bound we can apply these things for all the vertices in the graph. So by union bound we can say that for all the vertices in that graph, the degree of all those vertices is greater than log n is very low. Okay, so basically with high probability we can say that what the graph we are storing is at most the space will take is at most n polylog n. With high probability we can say that. Okay, by this lemma we can say that. Okay, so if this lemma we have shown previously, now we have shown that this can be done in polylog n space, which will maintain the streaming algorithm invariant. Okay, now we have to show that how many colors we have used. So this is nothing but this into this. These many partitions we have done. I mean, these many monochromatic graphs we have, and for each monochromatic graph we will use these many colors. We will use this many these many colors for each monochromatic graph. These numbers come from here. This number comes from here because we have seen that for every monochromatic graph out degree is at most this much quantity. So we have seen that for any graph with out degree delta out, we can color that graph using delta out plus 1. So these many partitions are there, and for each partition we use these many colors. So total we use this into these many colors, which is there is a calculation, so which is nothing but 2 plus epsilon into alpha, which we wanted. So we use these many colors. Okay, so that was the algorithm. So main theorem of this paper is given a graph with arboricity alpha and a small positive constant epsilon, there is a randomized this many pass streaming algorithm that finds 2 plus epsilon into alpha vertex coloring of the input graph using n polylogan amount of space. This many sparse is needed to get that partition of the algorithm, which was in the first part of this algorithm. So this is the main theorem statement of the algorithm. Okay. Okay. So here is the reference. And if you have any questions, then type in the comment section. Okay.